Okay, everybody, welcome back from the Thanksgiving break. I hope you had a great time. And welcome to our 12th lecture in ECE 576. This is going to be our second last lecture in the course. We're almost done with inference, the second unit in the course. And today we are going to look at some techniques of inference. The one is the exact inference and the other is the approximate inference. And again, this is a very high level overview. Obviously, these are very detailed topics and we wouldn't be able to cover everything in here, but just giving you the idea of what inference is like. And if you, if you're faced with an inference query or question, what are the ways to approach the problem? Okay, so before we get started with today's lecture, I think I just want to say that your projects are due after the last lecture. So it's the week after. So let's say it's December 17th. So this is a hard deadline, and if you fail to submit by the deadline, then you are going to be penalized in the score, because the deadline for grade submission is soon after that, and I don't have control over late submissions, and I cannot accommodate any requests. So December 17. Okay, so remember, hard deadline. Don't come up with excuses and make requests that I cannot accommodate. And then, so this week you will have quiz 6. Sorry, it's quiz 7, I guess. And then next week, homework 6. All right, so we just have 2 assignments left, and then I will drop one quiz and 1 homework for everybody.
Sir, on the last quiz, you said you're going to make the change to the grade. You're going to drop 2 questions, right? I remember saying that on quiz 6.
Yes.
I don't know if you made those changes yet, because I don't see those changes on my grade.
Okay, I think I made for some of them, but let me. Okay, so quiz 6, yes, you're right. I will remove 2 problems.
Thank you, sir.
And if you still don't see it, just send me a reminder, just in case.
Okay, sir.
Okay, so this, and then last thing is the feedback, like course feedback. So everybody needs to fill in the course feedback online that has been shared with you on, I don't know which platform, but you must have received a link. Okay. So spare some time and whatever you feel, let us know. Okay, so today's lecture, as I said, will be covering 2 topics. One is the exact inference, and the other is approximate inference. So in many times, inference problems are complicated, and when it's possible, you try to do exact inference. And when I say inference, I mean you have a probabilistic query about the problem, assuming you had a graphical model representing the problem. and you're faced with a probabilistic question over that graphical model, then you really want to find out that conditional probability of something. So you can either do it exactly, or if that's not possible because of the complexity of the problem, then you can resort to approximate inference, and we'll see exact inference in more detail, and I'll give you a few pointers on how people do approximate inference for this lecture. And the next lecture, we can look at some estimation techniques, and that will be it for the course. Okay, so when I say probabilistic inference, I really mean to say that we want to find out a conditional probability query, for example, here, where I want to find the probability of the event Y happening, given E takes a value small e. So I already have some evidence E, and I want to find what is the probability that Y has occurred. And you already know that this can be expressed as the joint probability divided by the marginal probability of E. The question is, how do we find out these factors? Okay. So finding these out will require a kind of a marginalization over the other variables. So in this case, let's say W is a set of variables which includes everything except Y and E. So if if X is the, or the sky is the set of all the random variables, then W is the set of the random variables excluding Y and E. Okay, so now if I want to find the joint probability of Y and E, that's basically marginalizing the joint probability of all the variables over W, where W is everything except Y and E. Okay, I mean, that sounds a very familiar thing to do. And the second thing is the probability of E, which is again marginalizing this thing here over Y. Okay, so once we have these probabilities, we can just take their quotient, or we just divide them and find the inference query. Okay, an inference query can be in the form of, let's say the example here, which says, what is the probability of a patient having a disease given some observed symptoms are there? So something of that sort. If you had a disease and symptom graph, then you can find the probability of the disease given symptoms to kind of do the diagnosis. Now, I mean, all of this sounds very simple, but the real problem is, how do we marginalize over the variables? And if the graph is large, the problem is if you just naively marginalize over all the unobserved variables, you will need an exponential number of computations. That's where the bottleneck is. So the real question is, how can we do it more efficiently? Is there a more efficient algorithm that can help compute these marginal probabilities? And hopefully that helps us find the answer to our inference questions. Now, I can take an example of a hidden Markov model. I take this example here because it's a very simple Bayesian network, and model. And the graph of the hidden Markov model looks like this. Okay, where every X results in a Y, and then there is a sequential transition between the x's. So x1 goes on to x. So after x1, we have x2, and x2 leads to x3, and so on. So imagine that you had a digital transmission of bits, like 6 bits being transmitted sequentially, and then they are received at the receiver again as y1, y2, and y6. So that type of system can be represented as a hidden Markov model. Now, question is, given the received bits, can we figure out what the x, what x was transmitted? So one example query is the following. So can we find the probability of xn given y1 to yn? Right, that's an inference question here because we've already observed the outputs. Does that help us figure out what the input is? So to do this, following our previous discussion, what you eventually need to do is find the joint probability and divide it by the probability of this. Okay, and to do this, basically what you do is you kind of marginalize your joint probability density function of the entire graph. So you have this joint probability distribution, and in the case of a hidden Markov model, you can easily factorize it as a product of factors. And so if you sum it over x1 to xn minus 1, what you will get is this thing here. Okay, so so let's try to I mean, obviously you can sum it in a naive way, but that's going to require a lot of computations because every variable has maybe 2 values, 0 or 1. So you have to sum over all possible combinations, right? Which means x1 takes 0 and x2 takes 1 and x3 takes 0 and the next one takes 1 and so on. So a lot of combinations that you have to sum over. But there's a smarter way to do it, right? So smarter. What you can do is use dynamic programming. So what that means is you first of all use the factorization. So instead of the joint probability, for example, so here's some tricks that you can use. So for example, if you want to find this probability, you can just write it as the marginalization over xn minus 1 and the rest. So it's just introducing a dummy variable and summing over it. Okay, and the reason we will do it is the following. What we will do next is we will separate it. So this can be written as the probability xn minus 1 and the y's times the probability of xn and yn given all these. So it's a trick that they use. Now, the next thing they can use is the conditional independence property. So so any xn and yn are actually independent of everything except the previous one. So it only depends on xn minus 1. The rest you can just delete. So this this factor actually can be simplified as this because of the conditional independence. Next thing is they separate this factor. So you can further factorize it and write it as xn given xn minus 1 and yn given xn and xn minus 1. Again, this is the chain rule, right? So this is the, you don't have to remember all of this, but it's just to show you that there is a more efficient way if you just use some clever tricks here, which will kind of reduce your number of operations that you need to do in order to do this summation. So for example, previously, if you were to do the summation, you needed k to the power n minus 1 summations, where so k is the number of possibilities, right? So is the number of outcomes. So for example, 0 or 1. So if you just have binary outcomes, then k is 2, and you have to sum over n minus 1 variables. So your number of operations will be like k to the power n minus 1, which is huge if n is large and if the number of outcomes are large. Now, getting back to the dynamic programming idea, what you're left with eventually is the following. And you see now what we have to do is we are just summing over x n minus 1. So there's just one summation. So what you'll do is for n equals to 1, you initialize probability of x1, y1 as this, right? And then I mean, this is like a it's like completing this summation. So for every other n, you can use this formula, but if n is 1, your probability of x1 given y1 to yn will require this thing here, x1, y1, and this can be actually written as this. Okay, now when you do this, it can be shown that your running time or the complexity of operations is the order of n times k squared. Right, so the good thing is not k to the power n minus 1. So it's more of a linear time, right? So not exponential. So then it becomes become much easier to find the same joint probability instead of just summing it naively over all the n minus 1 variables. And the reason we've been able to do it is the structure in the hidden Markov model. So if going back to your Bayesian networks lecture, you can see exploiting conditional independence properties can actually help you make the summations more compact, more structured, and that helps you in the computational complexity. Now, furthermore, if you want to do mop inference, so this is something new. It's called the maximum a posteriori. Right, so a posteriori probability is the probability of x given y. Okay, so if you have the Bayes formula, right, so it's x given y times, maybe I can write it more clearly. So here probability of y is the prior, x given y is the posteriori, and y given x is the likelihood, and so on. So these are very standard names that people have for these probabilities. So if you want to maximize it, then again, you can, what you can do is, it's like writing this as the joint divided by the probability of y1 to yn, and then because probability of y1 to yn is a constant, so it doesn't matter in the maximization. It's essentially trying to maximize only this, only the numerator. Okay, and then maximizing a probability or something is equivalent to maximizing the log of that thing. Okay, the log is max fx is equivalent to the maximization of the log of the function. And the next thing is the factorization. So if you had the probability factorized, then the log will help you split it up. So in this case, the probabilities can actually be factorized into x1, y1 given x1, right? And then x2 given x1, y2 given x2. So if you, express it in the Bayesian network factors, then you will have this form here. So these are the xi given xi minus 1 and yi given xi. And this is summed over 2 to n. So depending on these probabilities, you can actually compute this maximization. Now, if it were a hidden Markov model, the maximization is actually simple. It's like solving a shortest path problem. Okay, so if you were to find the shortest path from the source to the destination, and you have this sort of a graph, then I'm not sure if people have seen this, but there's something called a Viterbi algorithm in digital communication. Okay, so that really solves the same problem. So what it says is, what is the maximum? So what is the maximum a posteriori probability of a certain x given the set of y's? So it means if you have received y1 to yn, what is the most likely x that was being sent? So that's a detection problem, and that's exactly solving this MOP inference problem. So I'm not going to give you the details. It's a whole algorithm in itself to figure out what the so what are the exact x's that are the most likely. But the whole idea is you will find out the most likely path of the sequence of x's that was sent based on the probabilities y1 given x1 and y2 given x2s, and so on. So these are called transition probabilities. So based on those probabilities, you can actually work out a path. So if you're interested, how do you do inference in hidden Markov models? I think Viterbi algorithm is something you should look out for. And essentially, that algorithm is going to give you exactly this probability here. Okay, so if your problem is of this form, where there is a Markov, there's a Markov transitions, then and it's two-layer, maybe it's half of it is hidden and half of it is observed, then the Viterbi algorithm is the way to proceed. Okay, now as we said, you know, half of the inference problem is how do you find the marginalization, meaning how do you sum over the joint probability distribution. So to do that, what you need to do is you figure out a variable elimination order. Okay, so for example, let's say you have a simple chain, right? So you have 4 variables A, B, C, and D, and you want to find out what is the probability of D, right? That's a marginalization. So first thing is you write the joint density. That's really a Bayesian network factorization. So just by looking at it, you can write it as the probability of A times B given A times C given B times D given C. And then you need to sum over A, B, and C, right? So you have to do this. Marginalization to eventually find the probability of D. So let's try to do it. So if you act naively, what is going to happen is this. So this is your probability of D. Do you see this? So this is D equals to 0, D equals to 1, or whatever, 1 and 2. So that means you have to sum over all the possibilities. So here's A1, and here's A2, right? The others are the same. Okay, so here only difference is A is 1, here A is 2, and then A is 2, and so on. So you have to go through all the possibilities of A, B, and C. So it's like 2 to the power 3 different combinations. So you can see here that you have like 4 and a 4, 8 terms that are added to find what the probability of D is for one case, and so on. But what you see here is that there's some repetition, right? So for example, you can see these two are the same, these two are the same, right? So you're just repeating this. Similarly, you have a repetition here. And repetition there. So it's a lot of repetitions, which makes the computation inefficient. So what can we do? So one way is to, as we do in arithmetic. So let's say, if you have AB plus AC, what you will do is you'll just say A times the B plus C. Right, so instead of doing multiplying by a both times, you will only multiply once. Okay, so the way to do it is to find out the order of summation that will reduce the number of operations. So if you were to do this summation, which is just the Bayesian network factorization, what you can do here is, if you move the first two factors here, and then move the summation inside, and then as follows. So let's say you push the summation of A here, and then next one is you sum over B and have the factors involving B, and then you finally sum over C. That will actually reduce your number of computations. And I think that's, in this case, it is the most efficient. So when you do this, what you will do is you combine all the terms that involve A and B and write it as a factor, which is psi1 of A and B. And when you sum it over A, you will have something which is only a function of B. So you will call it as tau 1B. Okay, so next time tau 1B will combine with the probability of C and B, and we are going to call it psi 1, B, and C. Okay, you can actually call it psi 2, right? And when you sum it over B, you will get a new factor, which is tau 2 of C, and so on. So essentially, this process is called dynamic programming, and your computations are inside out. So you will first find out the factors, then you will sum over A, and then use those factors and sum over B, and then combine them, multiply them first, then sum over C. So you're not summing out from the outside. And it's easy to see how this can actually reduce the number of computations. Now, important fact here is that the marginal inference can be NP hard in the worst case. And luckily, because of the structure in Bayesian networks, we can cache some computations and then store it somewhere and use it whenever it's next required. So the key idea is, can we have a good variable elimination order? So when we are summing over the variables, you're actually eliminating them sequentially. And if you have a good order of eliminating variables, then overall, the number of computations will be reduced, and you will have an efficient way of finding the inference queries. Now, a general algorithm to compute the marginalization in Bayesian networks and Markov random fields is given here. So for example, if you want to find the probability of Y, then the general thing is the sum and a product. So inside you have a product of factors, and outside you have a sum. And so this is a general way of writing it. Maybe it's not very easy to understand, but really the point is you have factors phi's, and it depends on what is the scope of phi and z, and so it's actually a factor of y, z and y, and when you sum over z, it just remains a factor tau. So same idea here, but written more complicated way. So I mean, you can actually look at example to help you understand. So if you have a Bayesian network, basically the phi is the conditional probability distribution, and it's really in the form of the probability of xi given x parents of I. Okay, so if you have I1 to n, basically that's the factorization of your Bayesian network. So here we have a product here, and then the sum is going to do the marginalization. And once you have it, I think conditional probability queries will require you to divide by some marginalization as well. So we can look at it with an example here. So for example, let phi x and y be a factor when x is a set of variables. So we have x as a set of variables, and this phi is a factor. Now, if you want to marginalize it over y, then what you are left with is tau of x, which is the sum of over y of phi x and y. I mean, this example is giving you some numbers here. So let's say we have three variables, a, b, and c, and you are marginalizing over b. So I mean, this first table gives you the probability a, b, and c, right? So for every a, b, c, you have a number here. And now this is really, yeah, I mean, I think it is a probability. It doesn't have to be, but yeah. So you have to make sure it adds up to 1. Maybe it's not. So I will just write it as a. So this is phi a, b, c. Okay. I mean, I'm just saying it is a factor because the numbers may not add up to 1. So in that case, it's not a probability. And it doesn't have to be because it's a factor, can be normalized later on. So the second table here is the, let's call it a phi a and c, right? So it's actually a marginalization over b okay, and actually I can write it as phi 1 and call it phi 2. So I mean, it's easy if you sum over b. So for example here, the first entry is by combining these two, because a is 1 and c is 1 here. So if you add these, then you're actually marginalizing over b. So you just add the two values and you will get this value here. And the same thing for the other entries. So if you combine the entries with the same a and c and a different b, then you will get a shorter table, and one variable has been eliminated. Now, the general algorithm is the following. So you have to first find out, or in most cases, you can obtain a order of elimination. So let's call it. So let's call the variable z, and they are in an order that you need to eliminate first. So you have to do it iteratively. So you pick the first variable, marginalize over it, and then you pick the second one, and so on. So yeah, an algorithm is given here in much more detail, but we can understand it with the help of an example. So let's say we have a Bayesian network, and the question is, what is the probability of getting a job? Now, we've seen this earlier in the previous lectures, that the joint probability can actually be factorized in this manner here. So you have variable, then a variable given its parents, and so on. So I mean, here the C, which is coherence, and I is isolated, but the rest are in the form of a conditional probability. So you have all these factors, and that's a way to write the joint distribution in a minimalistic way. Now, if you look at this, you have factors which involve different variables. So for example, phi c is the factor corresponding to this. Okay, phi d and c comma d is a factor corresponding to this. Okay, and then this is the factor here, and so on. So there's so many probabilistic factors. You can write them as phi functions. I mean, they are probabilities, but you can also write them as a factors. Now, so let's assume that we have a elimination ordering, which is the following. So we assume that this is given to us.
Is this just an arbitrary ordering?
I mean, in this example, it has been carefully selected, but finding an ordering is a separate problem. So you may have to use some other algorithm to find the best ordering.
Okay.
Right, but let's say we have an ordering first, then how do we do it? So let's say you first eliminate C, then D, then I, H, G, S, and L. So here's how the algorithm runs. I gave you the kind of the detailed procedure there, but we can understand it with the help of this example. So if you were to eliminate C first, what you're going to do is you will sum the factors that involve C. So, I mean, if you look at the set of factors, the first factor is phi C, and the other one is phi D, which involves C. So the only factors that has the variable C are these two. And when you sum over C, basically the two variables involved are C and D. And if you sum over C, then what you're left is tau 1 of D. So that's a new factor that you will obtain when you sum over C. Okay, so let's say all these factors are gone and you're only left with the remaining factors and the new factor called tau 1 of D. Now the next variable that you have to eliminate is D. So you combine all the factors that are involving D. The first one is the tau 1 of d, obviously. And then the other factor that involves d is this one, phi g of gi and d. So great. So if you combine these, you have three variables that are involved, and if you eliminate d, then you're left with g and I. So your new factor will have two variables, which is g and I. So your new factor will be called tau 2. Okay, so we have removed c and d from the problem. Now we have I. So again, we will list the factors that are involving I. So what we're left with is the tau 2 and two more factors. One is phi I, the other is phi s. Okay, so combining these three factors, we have three variables, g, s, and I, and summing over I will leave g and s pending. So next one is h, and the only factor that has h is the phi h. So out of these three variables, if you remove h, then you are left with g and j. So there's a new factor here. Okay, next one is g. So we have three factors, tau 4, tau 3, phi l. And there are four variables. So your new factor, tau 5, will have j, l, and s. Moving on, we're left with s. So s comes in tau 5 and phi j. And the new factor will be tau 6. And finally, for L, tau 6 is the only one left. So you sum over L, then you're left with tau 7 of J, and that is really the probability of J that we are looking at. Okay, so remember, we want to find the probability of job or probability of J. So we kind of use this elimination ordering and find the probability of J recursively and with the fewer amount of computations. Now, as somebody asked, is this the only way to do it? Of course not. If you use an alternative ordering, so if I give you the example where you first eliminate G, I, S, L, H, C, and D, then you see if you eliminate G first, then you have so many variables involved. And your new factor has so many variables, actually 5 of them. So if you're doing this, then you're not doing it more efficiently. You still have a lot of repetitions in your summations. Okay, as opposed to what we had. So we only had factors involving maximum of three factors or three variables, and then it's a much more compact than this new ordering. Now, our original goal is find what the probability of some variable y is given some evidence, and we said we will do it as a following. So we will find the joint distribution and then divide by the probability of E. Now, basically we have to do it for both of them. So for the numerator, we'll have to use some variable elimination algorithm. And again, doing that means you have replaced each factor, which is left over from what you sum over. So, I mean, this is some technical way to express all of this, but really the example clarifies how to do it. And finally, when you have the joint between y and e, you can further marginalize it over y to get the probability of e. Okay. Now, so let's try to find out what the complexity of the variable elimination will be. So for example, if we were using the elimination order that we saw first, we can take a very generic case. So considering we have n number of variables and we have m number of initial factors. In this case, we had a lot of them. Let's see. So it's 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so we had 8 initial factors and 3, 4, 5, 6, 7, 8 initial variables. So at every step, we will pick a variable xi and multiply all factors involving xi, resulting in a single factor psi I. Okay, now if capital Ni is the number of variables in the factor psi I, and let n max is the maximum number of those factors or variables, I mean, I'm talking about these ones here. So in this case, the maximum number is 4. Okay, so the runtime of this variable elimination is then the order of m times k to the power n max. So now k is how many values can the variable x take. As I told you, if it's a binary, then k is 2. And the key thing to remember here is that complexity is really controlled by n max. So the more number of variables involved in the factors, the higher the complexity. So if you go back, look at the alternative ordering, you see we have larger number of variables involved in the factors. So our complexity of summation is going to be larger. Okay. Now, I mean, looking at the complexity in a different way, we can use the graph theoretic approach. So if you want to look at the graph structure, we can say, you know, this Bayesian network can be converted into the Markov random field, right? So remember, we have to kind of add new edges whenever you convert Bayesian networks to Markov random fields. So in this case, I think this also is a new edge here. So that's the process of moralization. So if you look at the moralized graph, then elimination can be seen as a graph transformation. So when a variable x is eliminated, we create a single factor psi that contains x in all of the variables y with which it appears in factors. So what we do is we eliminate x from psi and replace it with a new factor tau, which contains all the variables of y but not x. So we can call this new set of factors phi x. So I mean, if we had a graph representation, what does it do? So for example, you were given this moralized graph, like a Markov random field, then if you remove c, basically you will kind of delete the variable c and all its edges. And the next time, if you eliminate d, then D is removed with all of its edges. And interestingly, when you eliminate I, because I was connecting G and S, so you'll have to put an edge between G and S. So that's called the fill edge. Because there's a factor that involves G and S. Remember, there's a tau of G and S. So if you remove the factor phi, I, G, and S, you will actually end up with a new factor that involves G and S. So G and S have to be connected. So previously, if you remove C, you don't have to do it because C is not actually acting as a bridge between any two variables. And then when you remove D, you still don't have to do it because it's already there. I and G are still connected, but when you remove I, then the G and S have to be connected. So again, I think this is just telling you how complex it is to do inference using a certain variable elimination ordering. So if you have to add a lot of fill edges, that means a lot more computations still need to be done. So if you don't need fill edges and some elimination ordering can actually do it without them, then that's the best one. So I mean, it's helpful to compare to elimination orderings, and it's not a way to find something, but essentially to tell you how good a variable elimination ordering is. So we can summarize the computation cost using a single graph that is the union of all the graphs resulting from each step of the elimination. And we call this the induced graph. And it's represented by I, phi, comma, this symbol here, and this symbol actually means the elimination ordering. So under a certain elimination ordering, you can have an induced graph. I mean, in this case, it is this one, right? So more complex an induced graph is, so if you look at the same example using the ordering, you know, these are telling you the factors. So I mean, this represents the phi, you know, C and phi DC. Right, so that's one clique. So for that, you have a factor and so on. So the way you eliminate it, you will find, you know, different shapes of cliques within this. Now, I mean, once you have an induced graph, again, induced graph is the following. It has all the fill edges in it. And fill edges come from the elimination ordering. Now, once you have an induced graph for some factors phi and the ordering, then every factor generated during variable elimination has a scope that is a clique in that induced graph. Okay, so I mean, that's clear because if you remove some variable, then what you're left with is a clique in that graph, and every maximal clique is the scope of some intermediate factor in the computation. So I mean, these are just for your understanding. I think it's not really something that you're expected to do, but it's good to know these properties. And again, the runtime is of the order this, where n max is the, so remember n max, it is the size of the largest clique in this induced graph. So it's the same thing, looking at this, looking at the number of factors and the variables involved, just a graphical way of seeing it. Okay, and again, the properties are the same, and the running time essentially depends on the n max. So how many number of factors are involved, how many variables are involved in each factor. So the one with the smallest number of variables will have lower complexity. Now, induced width is the number of nodes in the largest clique minus 1, and it's the induced width is defined as the width of the induced graph after applying variable elimination to the graph G using an ordering represented here. And there's another term called a tree width, and which is actually the minimum induced width under any ordering. Okay, so you have to find an ordering that minimizes this induced width. And again, that's a optimization problem, and it may not be easy to solve. So there's oftentimes some heuristics used to solve this and find the elimination ordering. Knowing the tree width is great because it helps you find the bounds on the best running time achievable by a variable elimination order on a distribution that factorizes over the graph. Now, I mean, this is the important point here, that unfortunately, finding the best elimination ordering is oftentimes an NP hard problem, and therefore you cannot easily find the tree width of a graph. So practically, many times, heuristic algorithms, could be genetic algorithms or so, can be used to find a reasonable elimination ordering for a graph. So, I mean, the good thing is you don't have to do it every time. So for a given graph, you can optimize its elimination ordering once. It may be a complicated algorithm, but at least if you find out what's the best order of elimination, then doing the inference is easier, because every time you can use that elimination order. Now, variable elimination was one method for exact inference. The good thing is it is exact, so you're not using any approximations. But sometimes, with the large and the complicated graphs, it may not be computationally feasible to do variable elimination. So the alternative we have is the approximate marginal inference. Now, let's say if you want to compute the probability of x1 given some evidence in a graph which has a joint probability of x1 to xn, doing this exactly can be NP hard. So we can resort to approximations and approximate inference. And nearly all of those techniques are either Monte Carlo methods. And when I say Monte Carlo, more precisely, there's something called Gibbs sampling. There's a likelihood reweighting. Markov chain Monte Carlo. And if they're not Monte Carlo methods, then there are variational algorithms. And by that, I mean mean field or loopy belief propagation. So you don't have to go into all of these details, but just to mention in a broad overview to really give you an idea of what is going on. So I'm not sure if people know what is Monte Carlo. Monte Carlo is really to generate samples and then averaging over those samples to find, let's say, expectations and other things. So for example, if you want to find the mean of a random variable, what you will do is you will generate samples of that random variable, and then you take the empirical average, and hopefully that average is close enough to the actual expectation. So I can show you an example of Monte Carlo later on. But so for example, let's write it down here. So for example, if t is x plus y, where x is a normal 0, 1, and y is an exponential with a mean 1. So what is the yeah, I mean, what you can do is, so let's say what is the distribution of z? Does anybody has an idea? I mean, x is a normal random variable with a mean 0 and unit variance, and
I suppose you could generate random samples for x and y pairwise, and yeah, find values of z and then average over them.
Yeah, I mean, not average, but what you can do is you generate them, add them, and then you can plot a histogram, right? That can give you the distribution of z. So that's a Monte Carlo method of solving the problem. So again, with a with an inference questions in hand, you can again use sampling and find the probability through that route. So okay, now so if you had a Bayesian network, I think it's easier because you have a structure to the randomness. So sampling can work. So for example, if you had a topological ordering of all the variables, I mean, you can, two variables, they actually lead to a third variable. right? Something like this. If you have that type of ordering, what you can do is the, the parents, you can just sample. So we can just assign them some random values, some realization of the parents, and then use them with the CPDs of the. Remember, this Bayesian network has conditional probability distributions tables. So if you are given some values of the parents, you can actually find the probabilities of the child node given those values. And then once you do this, you can keep moving forward to find the probability of the child given the parent. Okay, so that's the idea. So if you have some network, then UI is some assignment to the parents. That can be using a Monte Carlo method, like you generate random samples, and then you sample the XI, which is the child node from the CPD, right? The probability of XI given UI, and you can keep doing this for all the variables. So once you have a large number of samples, you can do inference. And if you saw your last homework, I think there's an exercise that leads you to a software tool, and there you do exactly the same thing. You sample from the Bayesian network and then do some inference. Right, so you can do probability queries using some sampling methods. Now, it's a brief introduction to Monte Carlo methods. So imagine you have a joint distribution of x1 and x1, x2 all the way to xn. How can you compute the marginals? So you have to write your marginal, which is probability of x1 equals to x1 and some expectation. Oops, so you write it as an expectation where this function is 1 only when x1 is equals to x1. Okay, and then this expectation can be written as a empirical sum. So empirical sum meaning it can be written as the sum of the function times the probability. So essentially these two are the same things, but one is the sample method, the other is the expectation, which is more of a mathematical operation. So for example, if you want to do it using samples, you generate the first sample, right? So this is the first sample from the probability distribution P of X. And then this is the second sample, and all the way to M samples. So if you have M samples, then your estimate of the expectation of f of x is the empirical mean, which is the sum over all the f for all samples xm, and you divide by m, right? And you remember the function f is 1 only when x1 equals to x1. So so it's going to give you an average of this average of these samples. And if the number of samples is large enough, then this empirical average should converge to the expectation. And that's the logic behind Monte Carlo methods. So, I mean, if you remember in your calculus courses, there is the something called the weak law of large numbers. Right? If you've taken probability, again, you'll see this idea used a lot. And this law says that if m tends to infinity and you do 1 over m, summation over 1 to m, function of xm is actually converges to the expectation of fx. Okay, so essentially this converges. So empirical converges to expectation. For large number of samples. Okay, so yeah, I think that's the level of detail that we will go for the part of inference in this course. I think there are a lot of techniques that I mentioned. One of them is Gibbs sampling, likelihood reweighting, Markov chain Monte Carlo. These are again very detailed and complex techniques, and doing it in a simple example is not possible. It's a more of a computational job. So you need a computer to generate samples and try to do inference. And I think that's hard to give you an example in a lecture, but I can try to give you an exercise to see how this works. So that will be it for the inference part. I think what we are left with is the estimation. Okay, so let me write it down. So so up till now we've assumed that probability distributions are given to us. Okay, and in practice, oftentimes that may not be the case. So how do we estimate? Distributions from the data. Okay, so I think for the remainder of this lecture, we can look at estimation of distributions. From data. So there are two main classes of methods. One of them are called non-parametric methods, and the other is parametric methods. So as the name suggests, parametric methods imply that you have a parameter involved. So there is a hypothesis about the distribution. And what you eventually end up doing is a maximum likelihood estimation also referred to as MLE, or you end up doing a maximum a posteriori estimation, or MAP. And if you talk about non-parametric methods, I think the first one is you may be all familiar with it, which is called the histogram, right? Histogram, there is no parameter. What you do is you really have a plot of, some x against some frequency, right? And if you divide the frequency, you kind of normalize it, then that becomes a probability mass function or a density function. There are several other methods. Again, these are fields in themselves. So you can have something called kernel. Kernel density estimation. And there are some spline methods. Right, that you can actually use to fit distributions to data. So here what we're going to do is look at some parametric methods. I think we can look at the most important one, which is the maximum likelihood estimation. So assuming that you have some random samples, so let x at x1, x2, xn be random samples from a distribution with parameter theta. Right, so theta is 1, but note there can be multiple parameters. Okay, so you can, for example, you have a normal distribution, it has two parameters, the mean and the variance. So, I mean, you can have a distribution with any number of parameters. And now suppose that small x1, small x2, and small xn are the observed values of x1, x2, and xn. The likelihood function is defined as the probability of the observed sample actually the joint probability in terms of theta. Okay, so for example, so what I will say is if if the observations are from discrete distribution, so or from discrete then the likelihood function L x1, x2, and xn equals the probability of x1 equals to x1, x2 equals to small x2, and xn equals to small xn in the presence of theta. And which is again simply the joint probability, which is probability I mean, I don't need to write something else here, but or I can say this is the okay, so that's really the joint distribution, and this is really the likelihood function. So in short form, we can say that the L of x vector and theta is the joint probability and theta, right? Now, if the observations are continuous random variables, then L, x, and theta is really the joint distribution. Professor, it's a joint probability density function. And as the name suggests, the maximum likelihood is really to try to maximize the likelihood function in terms of theta. So find out what theta is going to maximize that likelihood function. Of the parameter theta represented by theta hat MLE is the value of theta that maximizes L x theta. So a note here is, sometimes it is more convenient to maximize the log likelihood instead. As I said earlier, log is a monotonous function. So maximizing something is equivalent to maximizing the log of that thing. Right, so I can write this note that is equivalent to maximizing the logarithm of that function. Okay, so we can look at an example to illustrate this. So let's take the example of a exponential random variable. So given xi follows an exponential distribution with a parameter theta, and we observe samples x1, x2, and xn. What is the maximum likelihood estimate of theta? Now, xi follows an exponential distribution, really is saying that fxi of xi equals to theta e to the power minus theta xi. So that's the implication when I say xi, the ith sample follows an exponential distribution. Now to solve this, we first need to write down the likelihood function. So the likelihood function can be written as L x theta is basically the joint density, right? X1, X2. And it can actually be split up because of the assumption that the samples are IID. Okay, and this comes from the assumption so they are independent so if that's the assumption, then the joint distribution, which is the product of the individual distributions, can actually be written as follows. So it's theta e raised to the power minus theta x1 times theta e raised to the power minus theta x2 and so on. So eventually it can be written as the product I is 1 to n theta e raised to the power minus theta xi. Okay, so now from here, what I said makes sense because log of this function is going to simplify it. So instead of trying to maximize the likelihood, we can take the log of it and then maximize it. So the next step is the log likelihood. So it is log, natural log of L log the product theta e raised to the power minus theta xi, which can be, written as the log of theta to the power n e to the power minus theta sum of I is 1 to n xi. Right, so I mean this thing here is simply theta to the power n times e to the power minus theta sum of xi. Okay, and with the natural log, you can actually split it up. So it's going to be ln theta to the power n plus ln e to the power minus theta sum of xi. And this can be written as the n log of theta plus, or actually minus theta I is 1 to n xi, and the log of e is just 1. So that's your log likelihood. Now, question is, how do we maximize it? And the answer is simple. Take the derivative and put it equal to 0. So to maximize theta, we take so we have to take the partial derivative of with respect to theta, and it will be what will be n times 1 over theta minus the sum of xi. And we put it equal to 0. So from here, we will have theta hat MLE will be 1 over n sum of xi. Oops, sorry, it's n over sum of xi, which is equals to 1 over x bar. So therefore, the maximum likelihood estimator of theta is 1 over x bar. X bar is the average, empirical average of the samples, and you take the inverse, and that's what your maximum likelihood estimator is. So this means if you have a set of observations coming from a exponential distribution, the best estimate of its parameter would be 1 over okay. Now, you can take another example here about, let's say, a normal distribution. So suppose that we observed random samples x1, x2, xn, where xi follows a normal distribution with parameters theta1 and theta2. The question is, find the maximum likelihood estimators, or the MLE for theta1 and theta2. Okay, so I mean, when when I say it's a normal distribution, so what I mean is f xi of xi is 1 over square root of 2 pi theta 2 e to the power minus xi minus theta 1 whole squared over 2 theta 2. Okay, I mean theta 2 is the variance and the mean is theta 1. Now, first thing is the likelihood. So it's Lx theta 1 theta 2 is going to be the joint density. Which is again by independence, the product. So it's actually the product I1 to n of this 1 over square root of 2 pi theta 2 e to the power minus x1 minus theta 1 xi minus theta 1 whole squared over 2 theta 2. And this turns out to be 1 over 2 pi theta 2 n over 2 times exponential minus the sum of I1 to n xi minus theta 1 whole squared over 2 theta 2. Okay, next thing is the log. So ln L x vector theta 2 turns out to be n over 2 ln 1 over 2 pi theta 2 minus the sum xi minus theta 1 whole squared over 2 theta 2. This turns out to be minus n over 2 log of 2 pi theta 2 right? Or I mean, we can split it up further, say minus n over 2 log of theta 2 and then minus 1 over 2 theta 2. Yeah, that's a sum. So xi minus theta 1 whole squared over 2, oops, that's it. So so now we have to solve for theta 1 and theta 2 that maximize this log likelihood. So we can actually take partial derivatives. So the first one will be curly log with respect to curly theta 1, right? And then we can also do curly with respect to theta 2. So if you take derivative with respect to theta 1, you only have it in the third term. So it's going to be 1 over theta 2 xi minus theta 1, right? And this has to be equals to 0. And if you put take the derivative with respect to theta 2, we'll have minus n over 2 theta 2 plus plus 1 over 2 theta 2 squared, and then the sum as it is. So, I mean, you have two equations, two unknowns, and if you solve it, so theta 1 hat MLE is actually equals to 1 over n xi, which is x bar, and the theta 2 hat MLE turns out to be 1 over n xi minus theta 1 whole square. So that's the estimator for mean, and this is the estimator for variance. Okay, so you see that if you just had random samples and your conjecture is that they are coming from a normal distribution, then the maximum likelihood is a way to obtain the best estimate in the least square sense for the parameters of the distribution. I will give you another example here, which is the Poisson distribution. So suppose that we've observed random samples. So, I mean, we already have some samples, x1, x2, xn, where xi is from a Poisson theta. So find the MLE for theta. Okay, now okay, so first thing is the density distribution. So if now in this case x is discrete random variable because Poisson is a discrete distribution. So what I can say is that probability xi equals to x is e raised to the power minus theta raised to the power x over x factorial. And x is 0, 1, 2, and so on. So the likelihood function which is L x and theta is actually the joint probability, right? So it's probability x1 equals to x1, x2 equals to small x2, and so all the way to xn. So it's again independent and identically distributed. So essentially this can be a product. Okay, and the distribution we already have, which is e raised to the power minus theta, theta raised to the power xi over xi factorial, right? And this can be further simplified to e raised to the power minus n theta, and then product theta to the power xi and xi factorial. Now, again, next step is the log likelihood. So ln it's going to be minus n theta right plus. So the log of the product is actually the sum of the logs. So it will be a sum of the log of theta to the power xi over xi factorial. Okay, and again, next step, it can be broken down into a subtraction, which will be log of or xi log of theta minus log of xi factorial. Okay, so it turns out to be minus n theta plus log theta sum of xi minus sum of log of xi factorial. Okay, so final step is to do the derivative. With respect to theta, so it's minus n plus sum of xi over theta, and the derivative of the last term with respect to theta is 0. So all of this can be expressed as 0, and then from here, theta hat MLE is actually turns out to be summation xi which is again x bar here. Okay, so I just want to add a quick remark here that obtaining the maximum likelihood estimates may be convenient only in some special cases. For example, the exponential, normal, right, Poisson. But in general, you know, theta hat may have to be obtained numerically. Right, because here things are nice, you can take derivative and that's equated to 0. and we find the maximum likelihood. But if the distribution is complex, then you may have to optimize it using numerical methods. Okay, so this was it for the maximum likelihood estimation, but we can also look at the maximum posterior estimation, MAP. And again, I can give you a quick example on that. So let's first look at what is maximum posterior or MAP estimation. So so it has to do with the posterior distribution, which is the fx given y. It contains knowledge about the unknown quantity x, and one way to obtain an estimate x is to maximize the posterior. So in general, the definition of posterior estimate is the the argmax over x of fx given y of x given y. Okay. Now this can be further written as the argmax of x using a Bayes rule, fy given x, y given x times fx of x over fy of y. So, I mean, this thing here is independent of x. So it can actually be removed from the optimization. So essentially, this is just the argmax of fy given x times fx of x, right? Or equivalently, the joint distribution also. Okay, but in any case, you depends on what is given to you. I can give you a small example here. So let x be a continuous random variable with the following density function. So the fx of x is 2x. X is between 0 and 1, and is 0 otherwise. Okay, so what it means is, that the distribution or PDF, that this is x, this is fx of x. And if it is between 0 and 1, it is 2x. So it will be 2 here. Right, so that's the PDF of x. And what we are given is also assume that y given x equals to x follows a geometric distribution with the parameter x. So again, this means that f y given x is basically 1 minus x to the power y minus 1 times x. So that's the density function of y given x. Now, the question is find the map estimate of x given y equals to 3. So, I mean, we can go back to our definition of x hat map, and it's the argmax of x of f y given x of y equals to 3 given x times fx of x. Okay, and then we can substitute these values. So what is the fy given x given that y equals to 3? So it turns out to be 1 minus x to the power 3 minus 1 times x, and fx of x is simply 2x. Okay, so it turns out to be the argmax 2x squared 1 minus x whole squared. So now to maximize the argument, we can take derivative. I'm taking the derivative, so it's d over dx. It's going to be 2 outside. Then we have x squared, and then derivative of 1 minus 2. So it will be 2, 1 minus x minus 1 plus 1 minus x whole square times 2x equals 0. So it will be minus 2x squared plus 2x 1 minus x squared. The 2 can go away, and the x squared can go with the x. So we're left with 1 minus x equals okay, so this turns out to be
Question on the second line there. I think we forgot to square the whole term on the right? Or did I miss something?
Which term on the right?
From the first line, we had 1 minus x in parentheses squared, and then on the next line, the squared is only on the x and not 1 minus x.
Oops, here, right? Is it?
Yeah, I think that's correct now.
Yeah, okay, so yeah, correct. So yeah, correct. So x equals, so then this can go with this, x equals 1 minus x, and then this will give you x hat MAP equals to 1 over 2. Okay, so that's the MAP estimate. So what essentially means is if you had a posterior distribution where this is x and this is f, x given y, and you had a, so you're trying to actually find this this value that kind of maximizes the posterior. So it's like detecting what was the most likely message sent, right? If X was sent and you received a Y, and you try to kind of figure out what is the most likely X that could have been sent. So that's the idea behind the map estimation. So I mean, ideally, this sort of a problem occurs when you're looking at you know, digital transmissions. So if imagine you have a binary transmission, and just write a motivating example. So let's say you want to make a map detector for binary transmission. Under a Gaussian noise. So what happens is, let's say you have two symbols, x1 and x2, and this is fx given y. So basically y is your x plus n, right? Whatever you sent, there's some Gaussian noise added to it. So if you figure out the y given x and the x given y are both Gaussian. So y given x is Gaussian, so x given y is also Gaussian with some normalizations. So imagine if you had x1 here and x2 here. So the densities are the following. So this is, it's a normal distribution. Right, so these are x1 and x2. Now, if you received, so this is your x observed, then, you know, the x that maximizes the posterior is x1 here. So most likely you are going to say it is x1 because x1 is the one with the higher posterior probability. But if you received something here, then obviously you're going to say it's x2 that was sent. So there's this line here in the middle. It's kind of this separation line. So anything on the left of this is going to be detected as x1, and anything on the right is going to be detected as x2. That's one application of MOP estimation, and it's widely used in digital communication where you have constellations. So you send some messages and you receive something else, and then you try to kind of correlate it with the inputs, and most likely it is in the form of a map detector. So I think this is a very useful technique for detection and estimation, and we have seen mainly two forms of them, but again, there are non-parametric methods also. I forgot to write one more. I think there's an expectation maximization also, so I can go and mention that as well. But we haven't covered it, and probably it's not part of the course. So that's the kind of end of the lecture today, and I understand that there's a lot of complex material we have seen today, and but all of this doesn't is not going to be tested. I think what you really need to understand is the higher level ideas. So for this week, we are having our quiz. So quiz homework is already done. So quiz will be seventh one, right? So the topics will be simply Markov random fields, right? MRF, and you know, high level. Maybe not. I mean, I think mainly the Markov random fields and Bayesian nets. So, I mean, more focused toward Markov random fields than Bayesian networks. And we only have one homework left, and that's going to be on estimation. So mainly likelihood estimation and MOP detection. So that's it. I mean, the next lecture, we are going to focus on really an introduction on neural nets and machine learning, right? So some introduction to machine learning as part of this course. So this is going to be the final lecture. So brief intro to neural nets and deep learning. Okay, so that's going to be it for today. If you have questions, let me know, and otherwise we can meet next week.
Professor, when you talk about the MRFs, are you still talking high level concept?
I mean, so it's like, let's say you were given tables and you were given some factors. I mean, just like we had today, right? So for example, here we have these tables, can you marginalize and then find phi AC? So that kind of stuff. Not too detailed, maybe just some computations, but it should be straightforward, at least. I mean, if you understand the idea, then it should be pretty simple. And I think you have 1 hour, so you can always go back to the lecture and take a look, you know. But problems are not complicated, wouldn't require a lot of thinking. Okay, any other question? Okay, just one more thing before we finish. I think I think that's also related to the quiz. So yeah, basically, I mean, you have to look at how to compute so given a Bayesian network, how to compute conditional probability.
That's from the previous lectures, correct?
Yeah, it's more towards the previous lectures. Right? So it's like, I mean, obviously simple, but some people may not remember. Use Bayes rule, right? So the probability of A given B is asked. You can, I mean, you don't have to, but you can first use this. And then maybe use the help of some factorization. So if you have a Bayesian network, then the joint probability can factorize in a certain way. And with what we learned today, you can have a variable elimination ordering, right? Not ordering, but kind of you can push the summation inside. So if I give you more, I mean, something like this. I mean, this example is important. So if you have I mean, this is a very simple query, right? You want to find probability of D. How you can do it is you first factorize it, and then you sum over A, B, and C. And again, you can do it this way, but this is not easy. So what you do is you push the summation inside. So the way you do it is using this. Right. So I mean, but give it a try. I think it's it can be confusing, but at least try to understand this example, and hopefully you can do it for a simple case.
I got a question.
Yeah.
Do you have any like supplemental material you could recommend if we wanted to go deeper in on some of this stuff right here? I mean, it was pretty dense today, but you know, just to walk through this in a little more detail.
I can. I mean, this. I can give you a reference text to read more upon this topic. I mean, a bit more detail, like the textbook, right?
Yeah, exactly.
Okay, so when I post the lecture, I'll put a reference text.
Okay, thank you.
I mean, there you will find much more details, but here's just an overview.
Yeah, I figure for this course, it's not as important to get in the nitty gritty, but yeah.
Yeah.
Appreciate
Okay.
that.
Sure. Thank you so much. All right, then let's meet next week, and remember to fill out the course evaluations, which you might have, I think.
Yeah, we've got
Yeah.
them.
Okay. Perfect. All right, then let's meet next week. Have a great day.
Thank you.
Yeah. Bye.